We have a question from Saul. In the MBT model, all virtual realities require time loops. The larger consciousness system also has a time loop in the MBT model, albeit of a much shorter duration. Since the LCS is fundamental, not virtual, and dimensionless, could its time be linear rather than granular?
I think he means continuous rather than granular. No, it has to be granular. It has to come in increments because the way consciousness creates time is just taking a couple of its reality cells, is what I call them in the books, and just let it rotate from 1 0 1 0 1 0, make a metronome, make that a regular changing system, and then that becomes the clock. So the larger consciousness system, as he says, has a higher frequency. Okay, its 1 zeros are come a lot quicker. 1 0 1 0 1 0 1 0. You know, they come out real fast, where ours are 1 0 1 0. So it's just counts a lot faster than we do, has a higher frequency, which means that its time length, its increment of time, is very short. The time between a 1 and a 0 and a 1 and a 0, the time between changes gets very, very short. So it has the highest frequency loop, but every reality that is dynamic, and what dynamic means is changes with time. That's the definition of dynamic. So any model, any virtual reality, any simulation that changes with time has an outer time loop. The outer time loop says, and they don't all have to have the same delta t. Like the Earth's delta t is much, much bigger than the larger conscious system's delta t, where we don't need that much resolution. The delta t means I calculate everything that's happened in this dynamic simulation. It means things change in the simulation. Then I let one delta t go by and I recalculate how everything has changed. So something's moving and it's here, this delta t, next delta t it's here, next delta t it's here, next delta t it's here, next delta t it's here. And when you do that with very small delta t's, it just looks like smooth motion. If you do it with big fat delta t's, then it looks like jerky motion, like that. That's called resolution. If you have smaller delta t's, then you have more resolution, so you don't see the little starts and stops, the jerkiness. It's just all one smooth. You know, it doesn't start here and disappear and then come over here and then disappear and go to the next one. So in any case, that's where time comes from, Saul, is that it comes from this reality cell going back and forth between a 1 and a 0, and that sets the time for that reality. So our virtual reality has pixels in time and pixels in space. Now we're used to pixels on flat surfaces, like on our screen. We have a flat screen monitor. That monitor is broken up into little bits of height and width, little squares, and those are called pixels, and that's an area. But now think of a pixel as a volume. Okay, now go to 3D space, and pixels are little volumes, X, Y, and Z, not just X and Y. So you can move one pixel at a time in three-dimensional space, and that's as fast as you can go. Every pixel you move, every pixel at a time, you move over one pixel a distance. Now, when I say that's as fast as you go, you might be thinking, well, in one pixel at a time, you could jump 10 pixels of distance. But yes, you could, but now you're teleporting. You're disappearing at this pixel and you're reappearing 10 pixels over. So what I meant to say was that in moving contiguously through the pixels, just from one pixel to the next, not teleporting, as fast as you can go is 1 pixel of distance for 1 pixel of time. Now, in our virtual reality, we call that Planck's time is the pixel of time, Planck's length is the pixel of length. And that creates a resolution that's much, much finer than we need in our simulation. But that's just as far as our simulation could go. Our simulation could be at that level of detail, but there's no need to run a simulation at any more level of detail than is necessary.
I'm Tom Campbell. I'm glad you're here. I hope you're enjoying the content. If you do like our content, then you should consider being a Patreon member, because Patreon members get early access to our special content. You will also be able to get your questions answered by me in special Q&A sessions just for the Patreon members. And most importantly, your contribution as a patron member will enable us to produce the content that you're looking for. So thank you.
So ours is not run at that level, certainly not everywhere. So those areas of our simulation that are very coarse don't need much resolution. They're run at very low resolution. Those that need more resolution are run at higher resolution. The system's smart enough to run each segment of the simulation at the resolution that is best fitting for that piece of it. That's just better computer science, less wasted time.
So that is where you get the concepts of maybe omniscient. The LCS has a lot more time to observe things with
Yes.
that with that time space. That's interesting.
Sure. You know how we think about computers, and computers can only compute so fast. And we can say, well, this computer can do 1,000,000 cycles a second, just make up a number. So that means it can change things. It can change its bits, 1,000,000 times a second. So it can update. If it calculates something, it can take a step in that calculation 1,000,000 times a second. So that's how we think of, the time loop. Okay, now in our world, our physical universe, we have a delta t. And in the larger consciousness system, their delta t is about 1 billion times smaller. That's 1 billion. That's 10 to the 18th times. Now, and I don't know that as a fact. That's just in my books. That's just kind of, I put in numbers because people relate to numbers more. Not if you just keep it away from numbers, it becomes a little too esoteric. So I stick numbers in. So I don't mean those numbers to be absolutely, those are the numbers, but it's just a way of looking at it. So I put theirs as 1 billion times faster than ours. So when we do just one delta t, it can do 1 billion, 10 to the 18th power. It can do all of those calculations. So it's a lot faster than we are. Therefore, yes, it can do all sorts of calculations between our delta t's.
That's how you see some of the anomalies that happen. That's how things can be very discreetly or in uncertainty tweaked, things like that.
Yeah,
There's
if you look at the future probability distribution, we're looking at everything that is possible, and then the probabilities of that possibility. Well, you'd think, well, that's a lot. That's a lot of information to compute. And then when a choice is made that is not predicted, then it has to go back and refix the predictions it made based on it was doing A, and instead it does B. Now it's got to go back and change all the predictions it made based on B rather than A. Okay, and you think, gee, that's a lot of That's a lot of calculations. How could it possibly keep up? But then when you realize it does a billion calculations for every one of our delta t's, then you realize it's got plenty of time and plenty of computing power to do things
That recalculating
like that.
feature is super fast. Well, thank you, Tom. That's a really interesting answer. Thank you.